We have two NOs coming together. There's a little rate constant K1 above the first arrow. And for the reverse direction, we have K minus 1. So this is written as a reversible reaction. And it's forming an intermediate N2O2. In the second step, we have the O2 coming in, reacting with that intermediate with a rate constant K2. And it's forming two molecules of NO2. So now we can write the rates for each of these individual steps. We can write the rate for the forward reaction here. And so that's going to be equal to K1. And we have NO, two NOs, so NO squared. And again, this is a step or an elementary reaction. So we can write the reaction exactly as it occurs. We can write a rate law for that step using the stoichiometry of the reaction. For an overall reaction, you can't do that. It has to be experimentally determined. But for an elementary reaction or a step in a mechanism, you can do that. So we write it exactly as it occurs. So what would be the order of this particular reaction as written here? 2. And what about molecularity? It would be bimolecular. So we're just getting you used to some of these terms. Molecular. All right, so then for the reverse direction, the rate of the reverse direction would be equal to what rate constant? K minus 1 times what? Yeah, N2 O2. So what's the order here? 1. And what's this called? Yeah. So that's called unimolecular. Oops. Molecular. All right. What about step 2? What would be the rate here? And that is a clicker question. Okay, just 10 more seconds. Yep. So we write it exactly as written. So we have the K2 times the concentration of O2 times the concentration of N2O2. All right, so what is the overall order here? 2. And again, that would be the bimolecular. Let's put that up there. All right, so we have our two steps, and we've written rates for all of those particular steps. Now we're interested in writing the rate of the overall reaction that forms NO2. So let's think about what the rate of NO2 formation is. So in the last step, we're